Hello everyone, this is Viresh Kumar Singh. Let me show you the demo of my project. So as you can see, I have opened my VS Code here in which my Python server locally is running. I also have my LM Studio in which I have downloaded and loaded my Qwen-3-4B Instruct model. Now basically I have built a debater system. So currently I have set the topic to custom, life versus death. So let's see it in action. I think I am facing some problems. Let me run the server again. So till we are waiting for this server to start up correctly, let me tell you, you must have used voice to voice AI apps, but many of these systems only start to do something when the user has stopped speaking. But what I have built is a speculative inference. So I've implemented a parallel fast path which runs before you finish speaking. For example, when a user starts talking, real-time speech-to-text produces partial transcript every 300 milliseconds. Now, LLM starts generating from the partial transcript only, and due to it, LLM gets a head start of 1 to 2 seconds, and by the time we have to get the response, it starts to feel instantaneous. Okay, so yeah, back to the demo. I think the Python server is correctly loaded. Let me give it a refresh. Yeah. So yeah, let's see it in action. The end is the only thing in life that's truly guaranteed.
You're right. The end is silence. But silence isn't an end, it's just the absence of
No,
meaning.
no.
And
We spend our whole lives running from the one thing we can never escape, and that is death.
you're running from nothing. But life isn't about avoiding the end, it's about building something real while you still can. And that's the only truth worth living for.
So as you can see, it's trying its best to debate, and it's arguing in favor of life, and I am arguing in favor of death. Now, the interesting thing here is uh, the partial transcript that is being used. So in this project, as soon as the user starts speaking, we are generating partial transcript every 300 milliseconds, and LLM is using that partial transcript to generate responses. Okay, and that is the core part of this project. Now let me give you an architecture walkthrough of this project. But before we do this, let's understand some key things. So what is sound? Sound is just air pressure vibrating, and a microphone converts this sound into electrical signals, which is an analog signal. But to use this sound in a computer, we take a snapshot of the pressure level of this sound. Okay, so when I say 24 kilohertz sound, I mean 24,000 snapshots of this sound per second. Now we just can't send each of these samples because then it will be 24,000 samples per second. We can't send these many samples. So what we do, we collect these samples, and when we have enough of them, we send them at one time, and this is called buffering. Now we will do all of these things over a special communication channel which is WebSockets. It is a kind of bidirectional communication channel. It can send two types of data, text stream or raw uh, binary data. We are doing it through the raw bytes only. Okay. So yeah, let's get into the architecture walkthrough. So the first stage of this is this audio in.py file. Okay. So we have this audio input processor here. When we speak, our browser captures audio at exactly 24 kilohertz. Okay. Then the browser bundles these numbers, as I already told you. This 24 kilohertz actually is represented as a 16-bit number. Let me tell you this. And these stream of numbers is called PCM, pulse code modulation. Okay. So browser bundles these numbers together and ships them over a WebSocket to the server. On the server side, this file receives these bundles, drops them into a queue so that nothing is lost even if the server is busy. So this is the stage one of this project. In stage two, we do resampling of 24 kilohertz to 16 kilohertz in this function. Basically, we do this because Whisper, the speech to text model that we are using, was trained on 16 kilohertz audio. So if we feed it 24 kilohertz, it hears everything at the wrong speed, like playing a record too fast. So we are using a mathematical technique called polyphase resampling here. We are multiplying 24,000 by 2 by 3. So 24 times 2 by 3 is 16. So there is clean conversion from 24 kilohertz to 16 kilohertz, no quality loss. At stage 3, we have speech to text conversion. So this resampled audio flows into transcript.py file and it is running faster Whisper, a highly optimized version of OpenAI's Whisper model in a background thread. Okay. So Whisper is producing two kinds of output here, partial transcripts and final transcript. And the partials are what make the magic happen. They are the fuel for the fast path. Okay. At stage 4, we have LLM generation. So when this partial transcript arrives, speech pipeline manager decides whether to start the language model now before you have finished speaking. Okay. And if the answer is yes, it queues a generation request and a worker thread calls LLM inference worker and calls the LLM, which can be anything. It could be OpenAI, Olama, or LM Studio, like I am using it here. So streaming matters here. Rather than waiting for the full response before doing anything, the system starts processing the first tokens immediately. Okay. Then we go to the text to speech. Okay. We are using Piper as the text to speech engine here. Now, Piper's native output is 16 kilohertz, but the browser expects 24 kilohertz. So we convert again this 16 kilohertz to 24 kilohertz uh, by multiplying it by 2/3. Okay, and then we get the result as a stream of audio chunks ready to play. This server.py file picks up each audio chunk, base64 encodes it, converts raw bytes into a format safe to send as a text over the WebSocket, and pushes it to the browser. Now, on the browser side, there is a small program called Audio Worklet, which is running, and it receives those chunks and plays them through the speaker in real time. Okay, so this was the whole pipeline, and this whole pipeline is local, no cloud API calls, and everything runs on my machine. Okay, so the main interesting thing here is the fast path. Okay, so how is the fast path working here in my system? Let's see. Basically, step one is the completeness gate. So every partial transcript from the Whisper hits the score function here in the completeness gate code. And what is this? This gate is a pure rule-based filter, no ML. It is rejecting four categories of input. Okay. First is words with no argument content, like I guess, yeah, uh. Next are phrases that are grammatically complete, but they don't carry any real position. Phrases like maybe, I suppose. Okay. Also, we check for sentence that end in words like because, and, with, the. Okay. Also, anything under four words get rejected. So these are the things we do in the completeness gate. Okay. Also, then after we do this, we start the speculation, and LLM starts generating a response while you are still speaking. This is called speculative inference. And after this, we do the similarity check. So when you stop speaking, faster whisper produces the confirmed final transcript. The system compares it against the partial that started the LLM using a text similarity function. And crucially, this comparison focuses only on the last five words, not the full text, because the beginning of the two sentences is often identical. Comparing from the end correctly distinguishes them. Okay. So if the final transcript is close enough to the speculated partial, the LLM response keeps running. If it is not, then the generation is aborted and LLM will, like, system fires a new LLM call. Okay. So that's the complete system. 6 stages of audio processing, one speculative inference loop, and a recovery mechanism also, all running locally in real time. So thank you for bearing with me in this explanation.